Awesome. Okay. Thank you very much, guys, for the organizers for having me. It's a lovely early morning here in the UK. So yeah, as mentioned, I'll be talking about the the influence of long-range hopping on the topological properties of the SSH model. So just as a quick overview of the talk. So at the moment, I'm just trying to entice you all with some pretty pictures, but it'll go something like, we'll have a brief introduction to the SSH model and its topological phases. We'll then go straight into the model used and its SSH structure. We'll then go to some short-range limits and show some results, and then go into the long-range interactions and show some what I think are more interesting results, at least. So to begin with the SSH model, well, it can be thought of as two chains of atoms or emitters in some bipartite lattice structure with some unit cell made up of an atom or emitter from either chain. So we have some intracell hopping J1 prime, and we'll have some intercell hopping J1. And some lattice spacing A. So this model has a type binding Hamiltonian, where these angle brackets just mean the usual nearest neighbor interactions with these creation annihilation operators here. And just as a more of a comment, I'm not going to go into any great detail, but this Hamiltonian exhibits chiral symmetry, which will become important. Hamiltonian parameterized by K, this 2x2 structure. So in a thermodynamic limit, this completely describes our system. But so now we move on to, well, what do we really mean when we're talking about the topology? So what we look at here is the geometric phase. So the idea was introduced by Berry in the 1970s, that not only can a state pick up a dynamical phase in time, but actually it can also pick up a geometric phase in its own parameter space. So let's take the example of the ground state of this 2x2 Hamiltonian. And yeah, so our job basically is to check the topology of the state as we move around. So it's parameterized by K. We know that K is going to vary from 0 to 2 pi. This guy is going to make a closed loop as a result. And our job is to check the topology of that loop, essentially. Yeah, so this, on any sort of continuous space, the topology is just going to be the same of any sort of loop. It can just be contracted to a point, so it would be trivial, unless there is a singularity, and there is in this case at the origin. So basically all we're checking is actually whether this quantity winds around the origin or not. And I use the word wind purposefully. So this quantity is quantized to some integer of 2 pi, and this integer is often called the winding number. And it's a topological invariant in this case. So when J1 is less than J1 prime, nu is equal to 0, we have a topologically trivial phase. And when J1 is greater than J1 prime, I'm saying it's equal to 1, it can be any integer. However, in our case, we only find a 0 or 1 phase. So that's the topology side of things. So in terms of a topological insulator, the other criteria then is also whether we have an insulator. This is a little bit more straightforward. In terms of, we just check the dispersion relation between the two bands here. We then get the gap between these bands, and if we have a non-zero gap, then these together make a topological insulator. And that's just a quick introduction to the topological insulator stuff. Here is it's kind of a set of lecture notes of which I used, if anybody is interested, when I started out with topological insulators. So let's move quickly into the model that we used. So what we did was we coupled two-level atoms to an optical nanofiber. The nanofiber mediates the interactions between the atoms. We can see the bipartite structure of the chains here, where one chain is offset by some distance b, and we're going to change this distance b, which will change the interactions, and that's how we'll probe the topological phases in this case. So we have the two-level atoms can either, the emission can either go into the fiber, of which we set up the guided modes of the fiber, or of course in general it could dissipate, but just for now we're going to neglect this dissipation. So just to have it written down in the general master equation, the quantum optical master equation for such a system in terms of spins. But now we can actually equally represent this as a hopping problem in terms of hardcore bosons with these creation annihilation operators. And our hopping coefficients now, they end up being proportional to the sign of this is the propagation constant of this fiber. And this is just the distance in the z direction between atoms, between atom I and j. So just to comment, this ER is the radial component of the electric field profile function of the fiber. And of course, due to the periodic nature of this sign function, or in the distance between the atoms, all the interactions become significant now in this case. So this all-to-all picture really is warranted. Okay, so now let's have a look at some results. So in the short range limit, so we just manually set everything else to 0. In the nearest neighbor case, as we vary this offset, we find that we can move between these topological phases, between the winding number 1 and 0 phases. So the energy spectrum then looks, so we can see it's as a direct result of the chiral symmetry that I mentioned, that we have a symmetric spectrum about 0 energy. And also we get this doubly degenerate set of 0 energy states. Yeah, so as we might expect in this nu equal to 1 phase, we have an insulating phase. We also have an insulating phase in the winding number equal to 0, but this is just a regular insulator, whereas we have a topological insulator in this case. And in between, we have some phase transition where the gaps close. So what do these 0 energy states look like? Well, the population is exponentially localized on the edge of the chain. I've only plotted half of the chain here because it looks the same on the other side. There's a symmetry involved there. But as a result, they've been dubbed edge states, and the edge states are going to be the main sort of focus and result of this talk. So we show that as we vary the offset, we can move between the topologies, and we find these 0 energy modes for the winding number equal to 1 phase, also known as bulk boundary correspondence. And then away from this, the transition points, we have regular insulator and topological insulator phases. So now if we move to next nearest neighbor interactions, the first thing to note is that we break chiral symmetry. So the uneven interactions, the likes of J2, J4, J6 is what breaks the chiral symmetry. This doesn't actually alter the winding number calculation at all. Here I've only gone up to 0.5 because there is this this reflection in B, or this repeating nature. However, this does affect the energy levels. So we see here some edge states still being retained, but the symmetry and the energy is certainly lost. In terms of the insulating phases, then we have what I have here is a direct gap, which is when the minimum of the upper band is at the same K value as the maximum of the lower band. We have an indirect gap when they occur at different K values. And then, of course, we have no gap whenever we actually get pushed out of the insulating phase and into a metallic phase, of which case we lose the topological insulator phase, of course, because we don't have the insulating part to it, and we actually lose the edge states in this case. So here we directly see this breaking of the symmetry and the energy levels as a result of the J2. And this is actually in direct agreement with this work done by a group in Madrid, which is always nice to see. So now what do these states look like now? Well, after introducing next nearest neighbors, the population is still localized on the edge. It's been pushed more into the bulk, and it's not exactly exponentially localized now. There's a slightly more complicated relationship in here. And as a result of the breaking of chiral symmetry as well, we also have population from the second chain, or the below chain, the sublattice B, on this edge also. So as we said, the next nearest neighbors, it doesn't actually affect the topology, the winding number calculation. It does shift the zero energy modes, of course, and can also push us out of an insulating phase into a metallic phase, and we lose the edge states in that case. Okay, so conscious of time, let's just move straight into the long range interactions. So in this case, in the bulk, so this phase diagram of the winding number, as we vary the offset, but also the lattice spacing, where this AC value is just some critical value in terms of the propagation constant of the fiber. It turns out that this phase diagram is identical for any number of interactions. Well, I checked it numerically up to 99 nearest neighbors, and it's identical, which is slightly surprising. But the comment is that we have identical topology for all interactions in this case. So if we take an example now, for moving on of this value of A and value of B over A of 0.4, and we take, say, 13 nearest neighbors, which is more than has been looked at before, a larger number. Then when we retain chiral symmetry, so what we do is we manually set all J2, J4, J6 to 0, just to see what would happen. We retain this bulk gap, and we expect to have a topological insulator phase here, but when we break the chiral symmetry, we lose this insulating phase. So we don't expect to have a topological insulator here. Yeah, okay, and let's move into some more results then in terms of the edge states. So if we again retain the chiral symmetry, and we go to a large amount of atoms, well then there's no surprise, but we do have some zero energy edge states here. It's not for the full winding number equal to one phase, but that's just due to some finite size effects. And these states now look like, well, they're certainly localized on the edge, not quite exponentially so. There's definitely a more complicated relationship going on, but we have some population localized on the edge, and we have some an insulated bulk here, which again will be expected. And the question is whether you can really say that this is long range, because it's 13 nearest neighbor interactions, fair enough, but there are 200 atoms in the system, which is quite a large amount in comparison. So what we want to do now is look at a fully connected 13 nearest neighbor system. So we shrink it down to 14 atoms, and we see what we get. So we still find some edge-like states here highlighted in blue. I say edge-like for a reason. We see on the first and last side, we do get some a large amount of the population. We have absolutely no insulating properties here along the chain. But I mean, not only this, we don't really have a concept of an edge here because of the fully connected system. And so any regular techniques in terms of bulk boundary correspondence, they completely break down here. So if that's not interesting enough, let's see what happens when we break the chiral symmetry now. Again, for 13 nearest neighbors, we have, in this case, 200 atoms. Now, recall, we don't expect to be in a topological insulator phase here. And that's exactly what we get. We have no energy gap whatsoever when we have 200 atoms. The previous state here now certainly becomes a bulk state. There's no insulating properties whatsoever, and we're not surprised here that this is okay. The really interesting result is when we move to, again, a fully connected system, and we once again seem to get some, and I'll say edge-like states, to be very careful. And to me, they seem to be what I would say almost exponentially localized on the edges here. Well, okay, edges again on the first few sites and the last few sites of the chain, with some sort of insulating part of the chain in between. But once again, just to note this, the usual bulk boundary correspondence here completely breaks down. We can't use the usual techniques. Not only that, these edge-like states that are being picked out here occur not only in what was a winding number equal to 0, but not only a winding number equal to 1, but also a winding number equal to 0 phase. So it really shows that we can't rely on the usual techniques. So we have topological insulator-like states, knowing we're not in a topological insulator state, and we have some sort of gapped energy levels. And well, so the hallmark, of course, of these topological states is how robust they are against disorder. So we actually checked these states as well. And these states are actually as robust against disorder as if we had 200 atoms and nearest neighbor interactions, which is considered what we would consider to be the most robust. So this is the main result. I can't unfortunately give you any concrete reasons or as to exactly what type of state this is, whether it's a possibly new topological state. The word topological metal has been thrown around, but I wouldn't want to speculate without any sort of concrete proof. But yeah, I hope you guys find that as interesting as I did, because it was certainly not expected. I was expecting to completely lose, as we lost the topological insulator phase, to lose any sort of semblance of these states and the topology. So, I mean, with that, I'll conclude. Now we use the optical waveguide model, which behaved as an SSH model with fully connected interactions. We broke chiral symmetry with next nearest neighbors, and we showed that we can destroy the insulating phase and lose the edge states. When we moved to the long range, then the topology was independent of the number of interactions. When we retained the chiral symmetry, we kept some of the topological insulator phases. Then we broke the chiral symmetry, and we still somehow got some topological insulator-like states, but we know they can't be topological insulator states because that's not the phase that we were in. And now we have an open question, essentially, of how we can relate bulk properties to a system really without a bulk and an edge. So our usual techniques they completely break down. And we may need some new techniques if this is some new sort of topological state. And with that, I'll thank you for your attention, and any questions, please do feel free.
Yeah, thanks, Ciaran. There is one question in the chat window by Federico Roccati. The question is, how come the edge states in the case of 200 atoms do not have an exponential profile?
Okay, so let me just go back to, so in this case here, it's a good question. So the short answer is I don't know. And the reason I don't know is because you can't solve analytically for the shape of these edge states anymore. Once you go past basically something like 3 nearest neighbors, it just becomes almost impossible to solve analytically. So the analytics just become more and more complicated. essentially, and somewhere in there is a loss of there's a loss of the exponential shape, and this is what we get. But unfortunately, I can't say exactly why, because you can't actually look at the analytics.
Okay, thanks.
Yep.
Are there any other questions? There's somebody has raised their hand, Vikash Mittal. Is it from the previous talk, or is it? Do you have any questions? Okay, so I guess if there are no other questions, thank you, Ciaran.